All right, hello everyone. So in this video, I want to be going through three important concepts within the theory of vector spaces. So this is the concept of linear independence, of span, and of a basis for a vector space. And then at the end of the video, I'll be going through an example which deals with all three concepts at once. And we are going to be dealing with a rather weird example of a vector space, but that is deliberate because I want to take us as far away from the intuition of Euclidean space as possible, so that we really have to use the formal definitions and we really have to understand the concepts to be able to answer the question. Okay, so let's begin. The first concept we're dealing with is this concept of linear independence of a sequence of vectors in a vector space. And maybe the best way to I think motivate this is just by looking at what does the concept mean for just two vectors. So let's begin here with just two abstract vectors in a vector space. So we look at x and y. So we begin with this point, which is called the origin, and our vectors are then just arrows that point from the origin. And linear independence is already visible here. What it means basically, so these two vectors here are actually linearly independent. And the reason for that is just because if I continue the line of one of them, let's say the blue vector here, simply the red vector does not lie on that line. And that's really just the whole concept of linear independence. So I have to label this here x and label this here y. Then this picture here is saying that x and y are linearly independent. Okay, now there's an opposite concept, which is linear dependence, and that just means exactly what you would expect. It means that the two vectors lie on the same line. So for instance, if I have this vector here, let's call this z, then this would just be saying, because they lie on the same line, y and z lie on the same line here, we say that y and z are linearly dependent. I should put in EA here, and here we go. Okay, so this is the concept of linear dependence and linear independence. And so intuitively that's what the concepts are. But what is the meaning, the real mathematical meaning, the precise meaning here? Well, it's just given in this definition in the blue box. So it would just be saying for this vectors x and y, it's just going to be saying something quite precise, and that's going to be that if we take a general linear combination and we find that it adds to 0, the 0 vector, this 0 vector is what's the origin. So if we take a general linear combination here and we find that it adds to 0, then the only way that that could have happened was that, in fact, the constants here were equal to 0. So the C1, it's equal to C2, is equal to 0. Of course, if you take these two vectors y and z, and they lie on the same line, then you can form 0 from them in a non-trivial way. So let's just kind of see how that might work. Let's use yellow. So if y and z lie on the same line, well, in that case here, you would see that y is equal to some number k times z. And that would just mean that y minus kz is equal to 0. And the point is that this is a non-trivial combination, a non-trivial linear combination. Well, why? Because there's a secret 1 in front of the y here. And this k actually has to necessarily be equal to 0. Not equal to 0, sorry. And so this combination here is just non-trivial. So this here is a non-trivial linear combination. So linear independence is just ruling out non-trivial combinations which add to 0. Okay, and so that's the property. So we say that two vectors, x and y, are linearly independent if the only linear combination adding to 0 is the trivial linear combination. All right, so now let's get a bit more specific. Let's look at the primordial vector space. Let's say, what should we, let's take R2, it's the simplest of all. So the simplest vector space, R2, and let's take two vectors in it. And so let's take x equal to, all right, well, it's the 1st of June, so let's say 1,6. And let's take another vector here, another random vector. I'm looking at the time, it says 11:41, so we're going to put here 4,1. And let's check. Is this a, are these two vectors linearly independent or are they linearly dependent? Okay, well, to answer that, we have to consider a general linear combination, like of this form here in the green box. So let's see. Okay, let's suppose we have to, of course, always, if we're going to prove an implication, let me just talk a little bit about the logic here. To prove an implication, we always have to start with the premise, which is this, and then make some logical deductions and end here with the conclusion, which is this. That's how you verify that this implication here is valid. So this property, it is an implication of two things, and so to verify it, we have to first suppose the premise, which is what we're going to do now. And the premise here is we're going to suppose that C1 x plus C2 y is equal to 0. Okay? Now the 0 vector in R2 is just the pair 0, 0. So that's going to, we can actually just already replace the 0 by what it is specifically in R2. But the point is now we have to make some logical deductions and we have to try and end with the relevant conclusion. And that relevant conclusion is that C1 is equal to C2 is equal to 0. We have to try and get there somehow. All right, well, let's try and do that. So what we do from here is we have nothing else to do other than to replace x and y by what they actually are. So here we're going to have C1 times 1,6 plus C2 times 4,1. And we know that that's equal to 0. And now this is just going to tell us that, so the way scalar multiplication works in R2 is that the constant comes inside. And so here we're just going to get that C1 times 1 plus C2 times 4. So that's the first component. I'm just adding the first components here. I'm doing it in 2 steps. So that, and then the second component here is going to be 6 times C1 plus C2. That must be equal to the 0 vector. Okay, so I can erase this now. Okay. Now, here, this is just going to give us a linear system of equations. So let's see what that linear system is. So the linear system of equations in this case is just going to be obtained by equating the components. So we have that this component here must be, of course, equal to 0. And likewise, this component here must also be equal to 0, of course. The only way vectors are equal in R2 is if their components are equal. Okay, so equating components here gives us C1 plus 4C2 is equal to 0. And also 6C1 plus C2 is equal to 0. Okay, fantastic. So now we are just dealing with a linear system of equations, and we can solve it. So remember what let's try and always keep in mind what the overarching goal is here. We're trying to calculate what C1 and C2 are and show that they have to be equal to 0. Once we've done that, we are done with the question. So let's see if we can do that. Well, here, I'm going to show you 2 ways of achieving this. So the first way is very fast. So we're going to just rewrite this entire system as a linear system of equations. So here we have 1, 4, 6, 1 times this vector C1, C2. And this must be equal to the 0, 0. So the point of writing it like this will become clear in a moment. But just to convince yourself, if you compute this matrix multiplication, again, you're going to get that this vector is equal to that vector, and the meaning of that equality will be precisely this linear system. And that's exactly why we can actually do this. It's just because they mean exactly the same thing. Okay, now here's the main idea, is that if I look at this matrix here, this matrix here has a determinant, okay, let's call it A, then the determinant of A is not equal to 0, which means that it has an inverse. In other words, A is invertible. So that in this equation here, we can multiply both sides by the inverse. So we have here 1, 4, 6, 1 here and here, inverse times this. So what I'm doing now is just I am multiplying the inverse on both sides. By the way, I didn't mention why the inverse, why the determinant is non-zero, but it's really quite straightforward. Let's just check, right? So I multiply these 2 numbers, I get 1, and I subtract 6 times 4, and that's definitely not going to be equal to 0. Okay, so why am I saying C1, C2? Here should be 1, 4, and then 6, and then 1. And now, the point is that this times C1 and C2, the point is that the inverse here multiplied by this matrix is going to give us the identity matrix. And on this side here, I'm multiplying also by the inverse. What I do to the left-hand side, I do to the right. So here I have 0, 0. And the important thing is that I'm going to get 0 on this side. So this will just be 0, 0 again. And here, what I'm going to get is just the vector, this vector C1, C2. Because this here will cancel to the identity matrix, and the identity matrix multiplied by any matrix or any vector is just going to be that vector. So here we're just getting that 0, C1, C2 is equal to 0, 0. In other words, C1 is equal to 0, and C2 is equal to 0. And so look at what we've done here. Let's just zoom out now. We've supposed what we wanted to. We've taken a general suppose that we have a general linear combination adding to 0, and we've produced these logical steps here ending with a specific conclusion, and that conclusion is the one that we wanted, that the constants actually themselves were equal to 0. Okay, now, of course, I said there was going to be another way of solving this, or at least another method for doing exactly the same thing. And that is, of course, to take this system of equations and set up the augmented matrix here and solve the system of equations using Gauss-Jordan elimination, and you'll definitely get that the constants should be equal to 0, that C1, C2 are equal to 0. Okay, so just to go back up again, this is the concept of linear independence in 2 dimensions. In 3 dimensions, it's really very close to the same thing. But just to spend a bit of time motivating what it means in 3 dimensions, let me just clean up here a bit. So just give me one moment. So in 3 dimensions, we are not talking about lines anymore. Vectors are not going to be lying on the same line, but in fact, we're going to be talking about planes. So let's just see what the meaning is, and then very quickly run through an example. So we're back here, and now let's talk about what it would mean for 3 vectors to be linearly independent. Okay, well, if we have 3 vectors, let's say x, y, and z. So we have here, of course, always the origin. And now we have, okay, let's say this vector like this. And let's say this vector here. So this is going to be, let's say, x, and let's say this one's y here. Then we have 3 vectors. So we have this third vector, which is going to be the red one. Okay. Now this picture is going to say that x, y, and z here are linearly independent. And basically, the reason for this is that if I take any 2 of the vectors and I form the plane, so let's try and form the plane here. So the x and the y would form a plane that looks something like this. And the point is that the red vector, it doesn't lie on the plane. And that's what linear independence is going to mean for these 3 vectors. Firstly, that the x and the y form a plane, and secondly, that z does not lie on that plane. Okay, so for these 3 vectors, we say that x, y, and z are linearly independent. If, again, I take any any linear combination, and assuming that it adds to 0, then the only way that this could have happened was, in fact, that the constants themselves were equal to 0. Okay. So that's the concept of linear independence. Again, it's just saying if we make this assumption, if we take a general linear combination of these 3 vectors, find that it adds to 0, then the only way that that could have happened was that the constants themselves were equal to 0. Okay, let's go through an example in 3 dimensions here. Okay, so let's pick 3 vectors in R3. So we're going to take the sister vector space of R2. So we take R3, and we take 3 general vectors here. So let's take x equal to, all right, what vectors are we choosing? Well, let's take 1, 2, 0, because I don't know what else to do. Let's take y is equal to whatever, 1, 0, 3, and z equal to 0, 1, 4. Okay? And let's check. Are these vectors linearly independent, or are they dependent? I don't know. Let's check. So what do we have to do? Well, we have to, again, start with this premise here and make this conclusion. So we are going to start with the required premise. So we take a generic linear combination, general linear combination C1x plus C2y plus C3z, and we check that if this adds to 0. So we suppose that this adds to 0. And now we have to make the conclusion that all the constants C1, C2, and C3 are equal to 0. Okay, so again, the only thing we can do, what can we do here? Well, we're dealing with a specific vector space and specific vectors. So let's write, not general, let's write specific. So C1 times 1, 2, 0 plus C2 times 1, 0, 3 plus C3 times 0, 1, 4 is equal to a specific vector, the 0 vector. So it's this. Again, the way scalar multiplication works is that the constant here just moves inside to each component, likewise here, and likewise here. And then we can add the 3 vectors just as we normally would, component-wise. And the result is going to be just C1 plus C2 plus C3 times 0, of course just 0. And then the next component is going to be 2 times C1 plus C2 times 0 plus C3 times 1. So we're just going to get C3 here. Okay, good. And then lastly, we're going to have C1 times 0 plus C3 times C2 plus C3 times 4. Fantastic. So this vector needs to be equal to 0. And again, this gives us a linear system, just as in the 2-dimensional case. So what is the linear system? It is C1 plus C2 is equal to 0. And then 2C1 plus C3 equals 0. And then 3C2 plus 4C3 equals 0. This here can be again turned into a matrix equation. In this case, it just becomes this one. So 1, 1, 0, and then here we're going to have 2, 0, 1, and then 0, 3, 4. 0, 3, 4. Okay, so this matrix multiplied by this vector here, C1, C2, C3. This must be equal to the 0 vector. And again, we've turned our whole linear system into a matrix equation. So we can now use a very, very similar argument as we did earlier. Let's call this matrix A. So we call this matrix A here. And I leave it to you to compute the determinant of this matrix. But you can easily see that since the determinant of A is not equal to 0, let's actually just check. Why not check, right? The determinant here is going to be 1 times the cofactor at 1. So 1 times the cofactor at 1 here is just going to be -3, so we get -3 minus 1 times the cofactor at this point, which is just going to be 8. So it'll be -1 times 2. Let's just write it out. So -1 times 2 times 4 times 4 minus 0 times 1. And here this is -3 minus 8, which is -11. Okay, I think that's correct. But anyways, the point is that since the determinant is not equal to 0, this matrix has an inverse, and and we can make the conclusion. Exactly the same way as we did in the two-dimensional case. C1 is equal to C2 is equal to C3 is equal to 0. Just again, you multiply both sides by the inverse, and you'll get the vector C1 to C2, C3 alone, and that's exactly what we want, to be equal to 0. All right, great. So that's linear independence of vectors. Good. So that is all I really wanted to say about linear independence of vectors. So let's move on to the next concept here. The next concept is the concept of a span of a set of vectors. So this is not very difficult to see what it means intuitively. Span. Okay, let's see what this means in 2 dimensions. So we have 2 vectors. Okay, let's take, again, we're thinking of the origin as this dot here. Let's take two vectors as we did earlier. So we have this vector here, and we have this vector here. Okay, so let's call this vector here x. Let's call this vector here y. Now, what is the span of x and y? It's going to be a set of vectors. And what set of vectors? It's going to be the set of all vectors which are linear combinations of these two. So the set of all vectors C1 x plus C2 y, where these C's are just numbers. All possible linear combinations of these vectors. Now visually, what is this? Well, let's try and see. Well, firstly, x plus y is a linear combination. So definitely you're going to get the vector formed by their sum. So this vector, this yellow vector, will be there. But also I could have taken, I could have inverted x. So I could take this vector, that vector is there. I could have also added this to y. So that means that this vector is there. And I could have continued this process. I could have also have taken half x and added that to y. And sorry, let me just get this. Oops. Sorry, 1 second. I could have taken half x and added it to y, and I would have gotten this vector here, just by this parallelogram. And you can kind of see that actually, no matter which vector I choose, I could choose this vector here. It will be some linear combination of x and y. That's the point. All right. So that's the idea here is that all vectors which are obtained as linear combinations of x and y are what's called the span of x and y. So what is the span of a single vector? So let's say we're working in R2. So let's take a specific vector. So in R2, we look at a specific vector, let's say x, and let's say that's equal to 1, 1. Okay, so this just looks like this. So we're looking at this very specific vector here, 1, 1. Okay, so what is now the span of x? It's just a single vector now. Well, this is going to be all linear combinations. So all, let's use a different variable. Let's say t now, times 1, 1, because 1, 1 is the vector we're interested in, where t is just any real number. Okay? Now you'll quickly see that all such vectors are just the vectors which lie on the same line. So the line that is generated by this vector is what this span is going to be exactly equal to. In other words, this span here is just equal to the set of all x, y, such that x is equal to y. And it's as simple as that. Okay, good. Let's look at the same idea, but now for 3 dimensions. So, okay, let me just make some space. So for 3 dimensions, we'll do something quite similar. In other words, in R3. So we look at R3 here. So in R3, what are we going to do? Well, we're going to take, again, 2 kinds of vectors here. So let's choose, doesn't really matter again. I have choice paralysis. So let's take x equal to, okay, it doesn't matter. So we're going to take here 1, let's say 1, 1 is 0, and y here is equal to 1, negative 1, 0. Okay. And let's try to understand what do these vectors look like. So, all right, we have the usual 3-dimensional space and how it looks. So it looks, I guess, something like this. No, definitely not like that, but like this. Okay, so imagine this is 3-dimensional space. This here is x. Let's say this here is y, and let's say this here is z. Okay. Now, we look at the vector x equal to 1, 1. Yeah. So this vector x here has x component 1 and y component 1. Okay? So it's going to be this vector. That's, again, in fact, if you don't mind, I'm going to just change this, make this one z. Sorry about that. Just because I saw that the picture is going to be easier like this. Okay, and so this vector here is just going to be exactly this vector. So x will be this one. So here we have 1, and there we have 1 as well. So 1 and 1. And so this point here is 1, 1. So that's x. And the vector y is close to that. It's going to be going in the negative direction a little bit. So we go about here. So this is, it looks around about negative 1. And this vector points to this point here. Okay. Now, let's try to think, what are all the vectors which can be formed from these 2 vectors? Okay. What are all the vectors? Well, so what are all the vectors? Well, I'm sure you will agree. In fact, all vectors that just lie on the xy plane will be the general linear combinations of these vectors x and y. So all vectors that lie on the xy plane will be able to be formed in this way. And let's try and actually go ahead and prove that. So how could we prove that? Well, the claim here, we have a specific claim. Let's make the claim. The claim is that if I take the span here, the span of x and y, what am I going to get? I'm going to get, the claim is that this is going to be equal to just the xy plane. So it's going to be equal to all, let's say, AB, 0, where a and b are real numbers. Okay. So let's check. Well, we have to show generally. Firstly, if we take a general linear combination of these two vectors x and y, the component of that combination is the z component is always going to be 0, just because the component of x at 0 and the component of y at 0 is also equal to 0. Okay, so definitely we're having this. I hope you'll agree, but otherwise please verify for yourself. Okay, so we definitely have this, but why the reverse? Well, let's check. Let's take a general vector. We want to try and see, for a general vector, a, b, 0, we want to see, is this in the span of x, y? Well, this has a very specific meaning. The span is what? The span is the set of all linear combinations. So for this vector to be in the span, right, for AB, for where A and B are general numbers, for this to be in the span, it's exactly the same thing to say that this AB here is equal to some linear combination S times X plus Y times T times Y. Okay? So that's the meaning. There exists this S, there exists this T such that this is equal. And again, this has a very specific meaning. This is the same thing as to say that AB 0 is equal to, okay, S 1 1 0 plus T times 1 negative 1 0. So that AB0 is just equal to, again, I'm going to add the components here and get what we need. So here we're just going to get S plus T, and here we get S minus T, and here we get 0, just for the same reason that I said earlier. And now this again becomes a linear system. And let's see what that linear system is. It's just going to be saying that S plus T is equal to A, and S minus T is equal to B. This here is a matrix equation. 1, 1, 1, negative 1 times ST is equal to AB. And again, for the same kind of argument, what are we looking for here? We're trying to show that there is an S and there is a T which make this equation here true. In other words, we can solve this equation for S and T. Can we solve this equation for S and T? That's the question. The answer? Yes. The answer is yes. Why? Because the determinant here of A is not equal to 0. And so this just means that, in fact, ST is exactly given by A inverse times AB. Simple as that. And A inverse is, of course, the inverse of this 2 by 2 matrix here. We don't even have to go further. We don't have to say exactly what A inverse is. We just simply have to prove that there is this S and this T. Now, what have we shown here? We've shown that every vector of this form is in the span. Since this is always true, at the bottom here, this is a true statement, A always exists, so S and T is always solvable. Up here, this is always true. So that means that we get this reverse inclusion, and so that the equality actually holds. Okay, so that just tells you a little bit about what span is for three-dimensional Euclidean space. In general, the arguments are going to be very, very similar for Euclidean space. So I just give you the dimension 2 and dimension 3 arguments here. Okay, so let's move on to the next concept here, which is this concept of a basis for a vector space. Again, a picture says 1,000 words, so let's see what the picture is. Well, let's go to, again, the mother of all vector spaces, R2. And let's take a look. Right, so in Euclidean space, we have two very important vectors. In physics, this vector along the x-axis here is called I, and this vector along the y-axis here is called J, I think. And okay, in symbols, let's be a bit more exact here. I is equal to 1, 0, and J is equal to 0, 1. So the important thing about these two vectors, these are two vectors, right? Now then, it's very easy to see, by the way, that these are linearly independent vectors. Of course they are. The line produced by y is the x-axis, and of course J does not lie on the x-axis. So these are linearly independent by the intuition that we saw earlier. They're also they have this very important property that every vector in our vector space, let's say, for instance, let's just take this vector here, okay? So let's imagine that this vector here, oops, sorry. This is a point, not a vector yet. So the vector that points from here to here, let's call it xy. So in other words, this point here is x and this is y. Then the important thing is that every such vector xy is equal to a linear combination of I and j. It's equal to x times I plus y times j. So in other words, every vector in our vector space can be produced from the vector I and the vector j by some linear combination. And so they have a very special role to play. Now, that special role is the role of being a basis for R2, okay? But not just I and j have this property. There are other vectors. Imagine I take I and j and I create a new set of vectors. So for instance, okay, let's just say we have our Euclidean space here. Two-dimensional Euclidean space. Again, we take I and j, but let's rotate them slightly. So let's say this vector here was just, I rotate j clockwise by whatever it is, 30 degrees, and I rotate I by 30 degrees. So this is, let's say, j prime, and this here is I prime. They are going to have the same property. Firstly, they're linearly independent, obviously, because again, the line produced by I prime, j does not lie in that line, j prime does not lie in that line. And secondly, if every vector here can be produced by a linear combination, then of course the same thing can be true here. Every vector that's rotated by 30 degrees or otherwise is also going to be obtainable here, so it will be obtainable here. All right, so what does that mean? That means that that property, that these two vectors are, that every vector can be produced from these two vectors, it's also shared by these vectors here. So there's a general definition needed, and that's the concept of a basis. So we say a vector space, if we give two vectors, b1 and b2, we say that these form a basis if, on the one hand, they're linearly independent, and two, the span of these two is equal to the entire space. Now, our space is R2, so here we would have to say exactly R2. So basis for R2. Okay, now this definition here easily and quickly generalizes to any vector space. And that generalization is just given up here. That's this general definition. So these vectors, n of them, form a basis for our vector space if they are linearly independent and their span is the entire space. A quick exercise. Can we think of immediately about a basis? What is a basis for R3? Well, let's check. If I'm in 3 dimensions, so let's say here's my 3-dimensional vector space. And just as I said earlier, I said this was y, and this is x, and this is z. We have 3 important vectors here. We have this vector, I. We have this vector here, j. Then we also have this other one, k. In physics, it's I, j, and k, I think. So these 3 vectors have the same kind of property. X, y, z is any vector, which is of the form x, y, z, is just equal to x times I plus y times j plus k times, sorry, not k, z times k. These are, of course, linearly independent. I, j, and k are linearly independent. And also, they span the whole space, which is what this little argument here is showing. So, in other words, the set, I shouldn't say the set, just the vectors I, j, k form a basis for R3. So that's very good. IJK form a basis for R3, and so we see 2 instances of this concept of a basis for a vector space, but they're all very familiar. So you can imagine, of course, what would you expect the basis in Rn to be? Well, there is something called the standard basis. The standard basis for Euclidean space, you can Google it if you like. It's I think, a very obvious thing you should see. But the point is that every vector space has a basis, which is an amazing fact, but it's true. Every vector space has a vector space. Well, it actually depends, by the way, if you believe in certain foundational assumptions in mathematics, but I think you will agree with what's called axiom of choice, but anyway, it doesn't matter. So every vector space has a basis, and a basis is a very important concept. It's like the atomic vectors in a vector space. All right, now, by the way, interesting situation. Color actually is a 3-dimensional space, at least our human perception of color. At least the colors that you can see through this video. So for instance, if I draw this color, here's yellow and it's pink and so on, the pixels that are rendering colors are rendering colors by just combining 3 vectors of color. They are, let me be more clear here. Color on a screen consists of 3 different numbers: the red component, the green component, and the blue component. So actually color is a 3-dimensional vector, and the basis is red, green, and blue. So anyways, that's interesting. All right, let's move on to an example. Okay, so let's take a look at this question here, and let's try to bring all the concepts together here with this one example. So we're given a specific vector space. Let me just elaborate a bit about what this vector space is. So the set here, the underlying set of the vector space, is the set of all cubic functions. So the set of all f of x, where f of x is cubic, which is just to mean this. Okay. Let me just write that out. So the set of all ax cubed plus bx squared plus cx plus d, all such functions such that 2 things happen. Well, let me just write that. The inflection point of f is at the origin. Now, what does it mean the inflection point is at the origin? It means two things. And let me just highlight what those two things are. It means, firstly, the function must cross there. It must go through the origin, which is what that means. And then also its second derivative must be equal to 0 at that point. Okay, why is this a vector space? Well, the sum of two cubic functions is of course a cubic function, but why should the sum of two such functions have these conditions? Well, it's actually quite easy to check. Let's check. If we have two functions, and we take a linear combination, let's say alpha f, in fact, let's just do this in 2 steps. If we take the sum f plus g, and let's evaluate that at 0, we need to verify this condition here, right? Well, very simply, this is just f of 0 plus g of 0. And that's of course equal to 0 because both of these things here are 0. Okay, so this is 0. So condition 1 is true for the sum of two such functions. Okay, well, what about the second condition? Well, if I take the second derivative of such a sum, I get this. And that's, again, 0 because of this. Differentiation is linear. So if I differentiate a sum of two functions, I get the sum of the corresponding derivatives. Okay, anyways, the point is that the sum of two functions in V is in V, and also you can check the scalar multiplication of two functions in V is again in V. All right, now let's try to get a bit of a better handle on what this, try to describe the set V in a different way. If we take a general f, general cubic function, it looks like this. Then its inflection point being at 0, or being at the origin, which is to say f is in V, is just the same thing as saying both of these conditions here. So f of 0 is equal to 0. But what does that mean, f of 0 equal to 0? Well, if I plug in 0, I'm going to get 0 here, 0 there, and 0 there. And that just means, at the end of the day, I'm going to get d is equal to 0. Okay? Now, if I take the second derivative of f of x, what is this going to be? Well, let's take the first derivative and see what we get. So I take the first derivative of f. I'm just going to get 3ax squared plus 2bx. And then I take the second derivative here of x, and I get 6ax plus 2b. And now if I plug in 0, I'm going to get just 2b. But if the second derivative of 0 is 0, then this being equal to 0 tells me something. It tells me that, in fact, the b has to be equal to 0. So in other words, if f is in V, then that's the same thing as to say that simply b is equal to 0 and also d is equal to 0. Great. So that means we can describe V in a different way. So V is actually just equal to the set of all functions of the form ax cubed plus cx. And as simple as that. A and c are in the real numbers. So this is the vector space. It's the same vector space. Okay, so in other words, if I can choose A to be anything, I can choose C to be anything. So out of this vector space, we can already see there's two examples. If I take my function x cubed, so the case a equal to 1, and I take my function x, these are two functions which have inflection point at the origin. But they also have another important point. That is that x and x cubed are linearly independent. And why is that? Well, these are linearly independent for a very simple reason. Because if I take a general linear combination here, cx plus c2x cubed equal to 0, this being equal to 0, it means it's equal to 0 for any x. So I can plug in x here, any x I like, and this will be true. So in other words, if I plug in x equal to 1, I'm going to get c1 plus c2 equals 0. And now I can plug in x equal to 2 and get another equation. So 2c1 plus 8c2 is equal to 0. And again, just as we were solving linear systems earlier, this will force the constants c1 and c2 to be equal to 0. You can do whatever argument you like. You can take out the matrix and see its determinant is going to be not equal to 0. I think it will be 6 in this case. So that definitely c1 and c2 are equal to 0. So if this is true, then c1 and c2 must be 0. So they're linearly independent. But moreover, just by how this vector space is defined, this is exactly equal to the span of the vectors x and x cubed. This is exactly the definition of the span of these two vectors. So in other words, what we've just seen is that x and x cubed, which are vectors in here, are linearly independent, and the span of x and x cubed is equal to the whole vector space. And this just means exactly what we wanted to say, that x and x cubed are a basis for V. It's as simple as that. Okay, so that does it for this video. So we've gone through the concept of linear independence, the main concept of a basis, and then this example here just gives you just the detailed calculation of how the concepts interact with this example here. Okay, thanks.